as you may know. And I'm dumber than most of your other teachers, so it takes me a while. But I'm getting there, coming along. What would you see if you could zoom in? You can't hear me, so you can't hear me when I say Tori's a lunatic. You didn't hear that at all? Can anyone else not hear me? All right. It looks like everyone can except for Tori. What are we going to do? How are we going to help Tori? What are we going to do to help Tori? Dylan, welcome. Glad you could be here. Do we have a message for all I hear is horrible audio. Is my voice that bad? Oh, okay. Tori, is your volume up? Question mark. Yes, there's a good idea. Go to settings, turn on your microphone. Wait, not the microphone, right? Because then Tori will be able to talk. I don't know, do something. Right. Am I recording this yet? Oh, yes, unfortunately I am. Speaker, yes, that's it. Thank you, Dylan. There's another option. You guys are so helpful. Man, it's a good thing you guys are here. Probably you should just be teaching this class. So you can't probably see my screen. Oh, you can, can't you? Where it says, what would you see if you could zoom in close? Can you still see my eyeball? That would be weird. On an atom. If you could zoom in super close. You know, it is kind of a hazel eye. You know, there's a song about that. She has her eyes, the girl has Lily's hazel eyes. It's from The Secret Garden musical. It's really good. It used to be my second favorite musical. I know most of you are young and you hate musicals because I always did when I was young. But I've finally grown to love them in my old age. Love me a good musical. I don't like the annoying ones, but I like the good ones. Joel could see the nucleus in my eye, the nucleus of the atom. 14. Man, you guys. You got your whole lives in front of you. It's so exciting. Oh, yeah, you know, I've never read the book. I only saw the musical. It's a good musical. You should try the musical. You probably like it. The mic says you're not muted, so it looks like Tori's still having trouble. Tori Bobori. Oh, I bet I know what the problem is. Nope. Maybe not. I'm just going to send a message to Tori real quick. And tell him that I don't know anything. That's really helpful, isn't it? Oh, maybe Tori's gone now. And I can't send a private message to him or her. Is Tori a boy? I don't even know if Tori's a boy or a girl, honestly. It's a good name for either one, but. All right, like I said, we're going to start class. So what would you see if you could zoom in close on an atom? I want some answers. Tell me what you could see And Joel already said the nucleus. What else? What do you think you could see if you could zoom in close on an atom? What would it look like? Electrons. Mm-hmm. Protons, neutrons, electrons. Empty space. Would there be a lot of movement? Like things moving around, or just kind of like this static, slow? All right, good. I like what you're telling me. I like what you're telling me. Now I'm going to tell you, though, the answer is, though all of you gave me very good answers based on the models that you know about atoms, you're all completely wrong. You wouldn't see diddly squat except for an occasional flash of light. Oh, good. This is what you might think you would see. Perhaps an atom like this. You guys can see those electrons floating around there. That's what we tend to think of, you know. But what you might really see is something more fuzzy, like this thing on the left, an electron cloud. We learned about the more updated models of the electron. Point out that the electrons more exist in sort of this cloud of probability, they call it. That's true, Given. Good point. I said if you could see an atom. Boy, you're right. No, but in this question, I said, what would you see if you could? Well, yeah, I said, if you could. Boy, you're right. I got to change my questions because that's, you know, it's deceptive. Darn it. There's always one of you that's smarter than me, and it just gets me every time. All right, anyway. But the point is, you can't zoom in far enough. You can't zoom in enough to actually see this. You can't see it, and I'll tell you why after this class is over. But literally, we cannot see an atom. All right, so just reminding you that online participation is 30% of your grade. Being here each week is an important part of that grade. In fact, I think some more people have showed up. Showed up? Someone correct me. Correct my English. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, I guess not. Still 11 of you. Is an important part of your grade. It allows me then to give you a reduced workload if you're here and participating. But I'm going to be paying attention to who among you is participating, because I need to see that you're responding, that when I ask a question, that you're giving me an answer, that you're involved in the chat, and that you're not just chatting to each other the whole time, or whatever else you might be doing. Right, I see there are copies. Thank you, Sam. You must attend class and participate, as I've said. If you miss class, you may watch the recording, and I think that the recording for this one will actually work, and you'll be able to view it. Although I don't think you'll see me, but you'll see the screen, and you'll hear me talking emphatically about all these things I'm talking about through the course of the class. And you may do that twice per trimester. Send me, what you're going to have to send me actually is sort of a summary of what we talked about in class, a summary of the class, just a short paragraph, which will give you, and you don't have to do it for week 1. So Harrison, week 1 is basically out because I couldn't even figure out how to record it because that's just how dumb I am. Or I couldn't figure out how to make it work usefully. So twice per trimester, 6 times a year, yes. That's that. How this class works is it's all in, what do you call this? Canvas. And you just go to the modules, that's what I'm trying to say, modules. There's a nice red color, that's nice. The last time I was doing this, it was gray. Section, and you start, I think all of you guys know this, you guys are experts on this. You guys have all started, you're doing great. Oh, except for one of you, whose name I shall not name. But there is one person who has yet to begin this class, who is actually here right now. But for that person, whose name I shall not name, please be sure you get caught up soon, now, right away, because this class is a live class. It's important to stay caught up and know what's going on. And I'm not even sure, because I haven't been able to contact you, whether you are actually, maybe you've been busy the first week of school or something. It's not Joel. Not this time, anyway. All right, next up, what do I do now? There we go. nor is it Tori. So then you'll see there's an introduction. Now there's even more. I've expanded this class so much. There's an introduction, which is a lot longer, which helps you set up your notes. And then there are these week one things. And for each week, though you can't see it there, you'll be able to see there'll be a section where you can watch the recording. For last week, it won't actually work. In fact, I haven't even removed that yet, and I'm sorry for not doing that because I haven't been able to make it work. But for this week, after this class, there will be a recording up there if you want to review anything, or for those of you that aren't here, you can come, obviously, and do that as one of your makeups. All right. And then you got your class notes. You guys already have that all set up, so I'm not even going to bother showing you that again. We're still working on atoms. And of course, matter, density, ions, and isotopes were kind of our words last week, but we're going to review that a little bit. Oh yeah. This is the roadmap for the semester. Atoms. Going to take about 4 or 5 weeks. Molecules, going to take about 4 or 5 weeks, and then we're going to end on a couple weeks of energy. That's it, man. That's it. So atoms, simply, protons, neutrons, electrons, the fundamental building blocks of all matter. The only thing that means that changes what everything around us, all the different things around us, are all just different types of atoms, often formed into or bonded with other atoms to form something called molecules. We'll see how all that works. Here's a couple of atom posters you might want to hang up in your room. Never trust an atom. They make up everything. Atoms consist of 99.999999% empty space. You might remember that. We talked about yesterday. If you blow the atom up to the size of a football stadium, the only real massive part of an atom, which is the nucleus, the protons and neutrons, would be the size of a pea in the center of a football stadium. Everything else, virtually, with the exception of the tiny little electrons flitting around the outside, the size of dust particles, would be empty space. That's insane, right? So mostly everything is not there. Whoa. And if we are made of atoms, then a scientist studying atoms is actually a group of atoms studying themselves. Whoa. Yes. The 0.00001% is simply the protons and the neutrons, as well as the electrons, the particles that make up those atoms. So everything around you is simply a giant bunch of empty space with these tiny little, very dense protons and neutrons. Well, he probably said that. You know what? He said that it would be the size of a marble. Remember, he went out like 500 yards. Remember, because he was in the desert or something when he did that, right? So he blew up a little bigger than a football stadium. You see what I mean? Oh, what did I do? What have I done? Oh, yeah. So who remembers what we did in last week's class? And while you're answering that, I'm going to run away real quick and grab something. Water, fire, gas. Whoa, dude. Somebody do some upside down? You can do that? That's insane. Sam, you're a genius. Party time. You guys can't party when I leave. Boo. So a lot of you weren't here, huh? Well, do you remember doing anything with this glass of water? Somebody wrote it down, I think. We destroyed some water, right? Hopefully you remember that. Did we talk about density? You guys remember talking about density? You are my density. How does that go? What's her name? I'd like to ask you to the Enchantment Under the Sea dance. Lorraine, Lorraine, you are my density. Has anyone seen that movie? Seems like most kids your age have seen that movie, but maybe not. There it is. Harrison's got it. That's right. I was in a gang once upon a time. It was a scary time in my life. I was in the density gang. We run around compacting things and people. So that's how we take care of people. We put them in the trash compactor to make them more dense, too dense. But dense is how much mass you can fit in a given volume. So it's m divided by v, m over v. Hopefully you all, that's right. Hopefully you all understand and can remember, can do this, literally do this with your fingers. Make this part of your life. Density equals mass divided by volume, m over v. When you see me in the halls at school, at Lego Club, at PE, as I'm crushing Joel at basketball, breaking his spirit, flash me the gang sign, and I'll give you a what's up. Uh-oh, Joel's mad. Joel's mad now. Another thing we did was we talked about destroying water. We destroyed water, did we not? Do you remember that? We hooked up a simple 9-volt battery. Ah! Don't lick them. You'll be shocked. That's right, we made bubbles. We separated the gas. Now this time I want you to look at the gas one more time, and I want you to tell me which side. See, this is the little side here is the positive side of the battery, and this big side here is the negative side. So the positive side will be here on this thing. So the positive side is the more silvery looking. It's going to be the more silvery looking of these two things. When I put it in the water, I want you to tell me which side is making more bubbles, because one side, I believe, you will see makes more bubbles than the other. Let's see how well I can do this here. Ah. All right, there we go. Bringing it up. Trying to make it so you can see it. Now, it looks like we're having a little trouble here. Just a second. I need to go put a little secret substance into my water. I'll be right back. All right, I promise you it was not an illegal substance of any kind. But salt does help water to conduct electricity a little bit better, so I put a little salt in there because it should help us to destroy this water a little more effectively. So here we go. Let's look again. Now you should see bubbles if I can move my fingers out of the way. Now can you see it now? You don't see the bubbles? The bubbles? Really? I can see them so well. Josh can see it a little bit. Let's try. Maybe it's the background. I'm going to put this down. Maybe you'll see it better if I put it in a different background. How about now? Is that better? What? You guys can't see it? Man, this is terrible. Let me see. Nothing? Not at all. You guys are lying. You're just trying to make my life miserable. I know how you kids are. Now I can actually see the video. Now I can see what you're seeing myself. You know, it's kind of, yeah, the background is kind of, oh, the computer reflection kind of hurts a little. Let me turn down that. That might help a little bit. Let's try this. Is that better? You see some? So which side is making more bubbles? Yeah, the side that's more silver or the side that's more like darker? Yeah, you can see all the little bubbles rising up from the darker side, and you can't really see as many. There are some, but not as many rising up from the silver side. Boy, I can just see it so easily. I'm surprised I'm sorry that you guys are having trouble seeing it. Yeah. So this one was putting up a lot more bubbles. We were destroyed. What it seemed that more water was being destroyed there, right? Well, that's not exactly how it works. How it works is because there's electrical current passing from the anode to the cathode, or actually from the cathode to the anode, I guess we would say, which is this direction. Then when the water is broken down, the hydrogen, which tends to be positive, attracts to the cathode, the H side, the negative side, and the, no, I got that wrong. Did I get that wrong? Oh, no, I think I did get it wrong, actually. The point is that it takes two water molecules to make one bit of oxygen gas. And it takes, and two water molecules, since they have two hydrogens, so if I draw another one right here with two hydrogens, they can make two molecules of hydrogen gas. So the hydrogen gas goes off, and from these two molecules together, you only get one oxygen that's bonded to each other. That's oxygen gas, so that's why there's O's in the middle. It's not eyeballs. But you would get two sets of hydrogen that are bonded to each other. Sorry, like Mickey Mouse. So you get one and two, because you can see if you break it down, you get four hydrogens that are total in those two water molecules, and there's only two oxygens in those two water molecules. So you're going to get more hydrogen gas than you are oxygen gas, a greater volume, though not a greater mass, because the oxygen actually weighs more. But you'll get a greater volume, and so you'll get more bubbles. That's why there's more bubbles on one than the other. Exactly twice as much gas, basically. Now that hydrogen gas, you may remember, if you set a match to it, will actually burn. Those bubbles coming out of that water. In fact, I've never tried that. Now I'm tempted. As those bubbles come out of the water, if I hold a match to it, I'm going to try this and see if I can get it to work, and then I'll show you guys next week if it actually lights it on fire. It does seem bad, but don't you want your science teacher to light things on fire? I mean, that's the whole point of going to science class, isn't it? All right. Well, next week, because I don't know where the matches are right now, and because I'm probably going to have to try this in a controlled and safe environment before I see exactly what happens, since I do not know what happens. I don't want to burn down my house. All right, so that's some stuff. That's what we did yesterday. But the point that I wanted to make to kind of add to what we did is that we're getting twice as much hydrogen gas because water molecules are always two hydrogens and one oxygen. If you add another hydrogen or take one away, you have something besides water, which usually tends to separate out from water. So that's why matter combines in these simple fixed ratios. You can see I've written that. I've written that. I wrote that. I've written that right up here. Simple fixed ratios. So whenever you have water molecules, if I break down and destroy all the water in this cup, I'm going to have exactly twice as much hydrogen as I have oxygen. because there's twice as much hydrogen in each water molecule as there is oxygen. It's 2 to 1. So you always have these simple fixed ratios when you have these molecular substances, because it's usually they're small things like carbon dioxide is 1 carbon and 2 oxygens. So if you break that down, then you have oxygen gas and carbon, which would be a solid, separated out of it in the same ratio, 2 to 1. Not everything is 2 to 1, though, of course, like carbon monoxide. All right, let's see what we have next. I actually didn't review this. I did. Oh boy, gotta get rid of all that junk there, don't I? We already talked about that actually, so I'm going to skip that. That's why, and this is why I have this here. Molecules are not like cookie dough because they don't just sort of combine, and it's still a cookie whether it has a lot of chocolate chips or a few. Molecules have exact ratios that are consistent throughout. Sorry, I do a lot of food analogies. It's kind of my thing. You'll get used to it. Atoms. So we've talked about atoms already. Atoms have protons and neutrons in the nucleus. That would be the green and the, would you call that brown things in the middle. And little tiny and very light, or not very massive, electrons around the outside in shells. And we'll talk about those shells as we talk about electrons more thoroughly, because that electrons in those shells determines how those atoms combine with other atoms and why they combine in certain ways. Now, there are different versions of atoms. So if you have an atom of oxygen, in other words, if you have something that has 8 protons, it is oxygen. That's what makes oxygen oxygen for some magic reason, which we don't even really understand. When you have 8 protons in a nucleus, you have oxygen. If you take a proton away or add a proton, you're going to get a totally different substance, like fluorine or nitrogen. If you add 2 protons, you're going to get neon. And all that's based on is the number of protons in the nucleus. All of the variety of things in the world around us are simply based on atoms which have different numbers of protons in the nucleus. Air, gas, solids, liquids, outer space, inner space, whatever you want to talk about, it's all atoms with different numbers of protons creating different types of things. Okay. But there are different versions of those atoms. So those atoms, even though it's still oxygen, could become an ion or an isotope. And those are 2 words I want you to remember, you're going to need to remember. An ion is simply an atom that has a difference in electrical charge. And the way that difference is generated is by changing the number of electrons. Electrons have the negative charge. You may know this, they're negatively charged. So that if you put electrons, when you stick your finger in an electrical socket, you get a bunch of electrons flowing through you, then it charges your hair, and that's why your hair stands up on end, because it's trying to get away from the other electrons. Whoa, whoa, whoa. Protons have the positive charge. So if you have 8 protons and 8 electrons, those charges cancel out. They are equal but opposite charges. So the way you get an ion is simply by adding an electron. So if I drew an electron in here, then I'd have 9 negative charges and 8 positive charges for a net charge of -1. Yes, I'd like you all to go put your finger in an electrical socket right now and come back and tell me what happened. Actually, I have a great story. This friend of mine, should I tell you the story? Do you want to hear the story? All right, this friend of mine, Paul, I went to teaching school with Paul. And Paul, when he was a little kid, he was at school, and he actually did stick his finger in the electrical socket, and he got, shocked. But it was, not very bad, and it actually seemed really fun. And so he was like, oh, I'm going to do that again. So he went back in for more, and he went back in, a 3rd time. But it kept getting, more and more harsh. And the 3rd time he did it, it was like, oh, that really hurt. I'm not going to do that again. So he kind of learned his lesson. Then, a couple of years later, he was in class, and he had the papers at his desk, and he was handing the papers back to the person behind him, and he hit his funny bone. And, you feel that thing in your arm. He'd never felt that before. He'd never, ever hit his funny bone before. And he instantly thought back to that moment where he stuck his finger into the electrical socket, and he said to himself, I now have like an electrically charged hand. That turned me into a superhero with electric powers. What am I going to do with my superpowers? Am I going to use them for good or evil? And he went through the whole like gamut of thoughts about what he was going to do just because he hit his funny bone. And then, of course, tried to use his powers, but could never figure out how to zap anything or do anything. So he never had to answer the question if he was going to be a good superhero or a supervillain. But it was pretty funny the way he tells the story. Anyway, so that's an ion, is when you have a different number of electrons, which changes the charge. Well, there's also things called isotopes, and that's when you have a different number of neutrons. So if I add another neutron to this mix, I'm not going to change the charge because neutrons are neutral, they have no charge. But neutrons weigh a lot. These particles in the nucleus weigh a lot. The electrons don't really weigh anything. So you're going to change the weight. And you're also going to change the stability, as we'll learn about neutrons, of that atom. And a lot of times there will be radioactive decay back to a simpler atom. So all you have to remember about ions and isotopes, I don't know how long it took him, Beth, but it took him, it was probably a few minutes, where he was starting to catch on like, okay, this isn't working. But I'm sure he tried it that night, like in bed and the next day or something. That's right. Unstable atoms can be radioactive, which means basically their neutrons are turning back into protons through some magic I'll tell you about later. So ions and isotopes, they don't change the number of protons because that changes the atom that you're dealing with. But they change the number of electrons in the case of ions, or neutrons in the case of isotopes, to create a different version of that same oxygen atom. Does that make sense? You guys with me? I'm making you into experts here. Experts on chemistry. All right. That's a really good question, Shay. That's an excellent question. And the reason that they're bigger than the protons is because we can't draw these atoms to scale. And so we just kind of draw them however we want. And so technically, those electrons are 1/2000th. They're 2,000 times smaller, in other words, or less massive than the protons and the neutrons. So it's just a model that's not accurate, that particular model. But that's a great question, Shay. And you'll notice that with the atoms, we can't make the models accurate because if we made a model accurate, we'd have to show something the size basically of this football stadium, but this whole nucleus that we have here would have to be, like I said, a pea in the middle of that football stadium, right? To actually be accurate to the size the nucleus is. And the electrons wouldn't even be visible because they'd be like particles of dust. So there's really not much point in trying to draw an atom to scale. There's the P right there. So we don't draw an atom to scale. So all of these models I'm showing you are deceptive. And Shay, you caught on to that, so that's good. Okay. So as we've already said, because it would be a P in the center of a football stadium, the nucleus, and the electrons would basically be no weight at all, the nucleus would be a P. So this whole bit here, the blue and red, the nucleus, the protons and the neutrons are called the nucleus, would be the size of a pea in the center of a football stadium if you blew an atom up to be the size of a football stadium. And that's basically all the mass of the atom anyway, which means the atom is 99 point blah, 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 blah percent empty space. And again, another food analogy, you'll notice. I'm trying to show you today how weird atoms are. That's the goal of this class today. Atoms are weird. We've talked about, and I'm going to answer the question of what you would see in just a little bit. But what's going on? I'm going to answer the question of what you would see, but I want you to understand some other things about how weird atoms are and how little we understand about them. In other words, I am, in a sense, trying to blow your mind today a little bit. All right. Now the next thing is, how big is an atom? And I'm going to use another food analogy. Grapefruit. How many atoms are there in a grapefruit? That's what I want us to think about, so we can kind of start to get an understanding of how big an atom is. How many atoms are there in a grapefruit? What would you say? Pick a number. Write a number down. How many atoms do you think are in a grapefruit? Like 100? Or a million? Or a billion? 10,000? Yeah, I don't know. Good guesses. I like it. All right. Well, let's think about how those atoms are, first of all, located inside of a grapefruit. Now, let's keep in mind, they're not going to be individual atoms. They're going to be formed into molecules like these. So one thing that's going to be confusing to you, and if you just pay attention to me, even if you're tuning me out for a couple of minutes, it's going to save you a lot of pain and agony, is when we look at atoms, we always represent them with these balls: neutrons, protons, electrons. But we also represent the whole atom as a ball when we put it into these molecules. So this first part's going to be about atoms of the class, the next part about molecules. But I want you to note that when we have an atom with these electrons and protons and neutrons, we actually just turn it into a big ball, like, oh, see, I can't do this. You're going to want to watch this. This intense, this is like a, what's that? I can't remember what they're called. Oh, Shay, you spoiled it. You spoiled it. Here's the other. So this is like citric acid. This is one molecule of citric acid. This is fructose, and these are different atoms. The gray, the dark gray, the light gray, and the red are different atoms. But the atom itself, we represent as kind of a ball, and then we put it, watch this, we put it inside of, and it becomes one of these balls down here, all by itself. So for example, if this was an oxygen atom, then this whole red ball down here in this molecule is an oxygen atom. So it actually has its own electrons, protons, and neutrons, that kind of thing. But if you couldn't see it, it's not that big of a deal. But this is one atom, including, and it's just we represent it as a ball again. So I just want you to kind of keep that in mind. The atom, protons, neutrons, and electrons represented as balls, and then the atoms themselves we kind of represent as balls. Well, you guys are having trouble, huh? We represent as balls when we put them in these sort of structures of models, again, of molecules. All right, so a grapefruit made of citric acid, fructose, which is sugar, things like that. But how many atoms are in there? Well, it's a staggering number of atoms. It's not even trillions. It's way beyond trillions. It's like quintillions of atoms. And it's the same number of atoms that if you, as Shay looked up because she's an astute student, if you filled the entire Earth with blueberries, another good example, the number of blueberries that would fit into the Earth, if you could fill up the Earth with blueberries, is the same number of atoms that there are in a grapefruit. So imagine how many, I mean, you can't imagine. It's beyond what you can actually make sense of. Oh, you watched the video of that? So if the atoms in the grapefruit were expanded to be as large as blueberries, it would be the size of the Earth. The grapefruit would be the size of the Earth. So here you can see filling the Earth with blueberries, that's the same as the number of atoms in a grapefruit. Man, I'm sorry you guys are having trouble with the, let me see if the, it seems to say that I have good audio connectivity, so I don't know if it's on my end. Yeah. All right, so the final thing is we know how small atoms are, and we know that they achieve the great variety of things around us, whether it's like the wood in a pencil or the plastic in my sunglasses or the water here or the gas that I breathe in, the oxygen. They achieve the wide variety of different properties simply by changing the number of protons that exist inside the nucleus. It's just a difference in the number of protons. There's no other differences in the substances around us. But next, we want to ask the question, why can't we see atoms? Let's finally stop for a minute. Well, the reason is because atoms are so small, as I just pointed out. If you can fit that many of them one grapefruit is made of that many atoms, then they are so incredibly tiny that the very concept of light doesn't even exist on the same, it doesn't function in the same way when you get down to things that small as it does on the macro scale. Because light itself, all of the light that you see or that's bouncing off of things that you see around us that enters your eye, is simply electrons jumping between orbits around the nucleus. So this is another example of an atom. And light is emitted when an electron jumps from an outer energy state to a lower energy state, a lower shell within an atom. That emits a packet of light, or a photon of light, as Einstein would have called it. And that's all that you see. So you can't actually bounce light off of one of these things to see what it looks like. And you need to bounce a lot of light off of it to see if it was actually a ball or what shape it was or anything like that. So we don't know what shape it is. We don't know what color it is. Shape and color may not really even have any meaning at this scale because we get down to things that are so tiny that they obey quantum mechanical laws, quantum physics. And so the smallest bit of light that you can get is the light that's emitted when an electron jumps from one state to another. And it's then absorbed, it absorbs a photon, and that causes it to jump up to a higher energy state. But that's what light is, and that's how light is emitted. So you can't actually shine light onto an atom because all that's going to happen is when you shine like a single photon of light, the smallest bit of light you can shine onto an atom, it might, if it doesn't just pass through the atom, which is 99.99% empty space, right? If it doesn't just pass through the atom, it might cause an electron to bump up to a higher energy state, but it's not going to bounce off the atom. It's not going to give you a way of actually seeing the atom or anything like that. So the very concept of sight doesn't even work when you get down to things as small as atoms and the electrons, protons, and neutrons that make them up. Crazy, crazy. All right. I'm sorry, I keep freezing. Thank you for coming to class today. I think that's about all I have. Let me see if there's any more slides I put on here. Yeah, it could be the internet connection. It could be skipping. Oh, the periodic table. I should point this out to you. You're going to learn about this. We have this coming up in your lessons coming up. But the periodic table is simply a way of organizing all of the substances that there are that exist in the world around us by the number of protons that are in the nucleus. So you can see that, let's see, actually I'll go real quick here. You can see that there are 5 protons in boron. If you add a proton, you get carbon. If you add another one, you get nitrogen. If you add another proton, you get oxygen. And all the variety of things around us are simply, subatomic particles. Quarks, up quarks, down quarks. No, we won't do that. All the variety of things in the world around you are simply derived from the change in the number of protons. But then you can see there are patterns in the periodic table based on how these atoms tend to combine with each other. For example, whenever you get to this point here, 2, 10, 18, 36, and you have a balanced atom that has that number of protons and that number of electrons, you're going to get the same type of properties. These are called the noble gases. And if we organize this periodic table, this table periodically, so that when we see those similar properties, we kind of start a new table, then we see that these groups of elements share similar properties. So the group 1, group 2 has similar properties. The metals all appear kind of in the middle here. These all tend to be gases over here, much more electronegative. And there are lots of other properties. One that I wanted to show you, though, because there's lots that you don't even think about, is simply melting point. So, for example, in this one, you can see the melting point of the elements for whatever reason. Oh, good, Beth. I'm glad that helped. The melting point of these elements tends to be the highest, or actually which element, based on its symbol, the 1 or 2 letter symbol, seems to have the highest melting point. Based on, you kind of have to read this graph. So you see that in Kelvin temperature, it goes from the coolest 0.95 melting point to the hottest, which is 3,800 Kelvin, extremely hot. Yeah, so some of the hottest ones would be W, which actually weirdly stands for tungsten. So right here, that looks like the darkest red, but carbon also. But you can see that melting point has these sort of congregation, like as you get closer to tungsten, as you move in that direction, the melting point moves up. So the periodic table has lots of things like this where there are trends in the periodic table. And also as you kind of get closer to carbon, it seems that melting point goes up. How can you get the atomic number for the assignment on the 15th? Look it up in a periodic table, probably. Oh, really? A tungsten wedding ring? Nice. Another example of a trend in the periodic table, which is similar to this one, is, wait for it, there it comes. State of matter. And this kind of has to do with melting point, but you can see that at, for example, at this temperature, 322 degrees Celsius, there are a certain number of elements that are a gas, and they're all sort of over here. So again, this is another trend that you would see. There are a certain number that are a liquid, and they all tend to be either on this line over here or kind of in this area here. And then there's a certain number that would tend to be solid at that. And again, here's another sort of trend that you would find in the periodic table. All right. Tungsten drills. Oh yeah, I used to work at a machine shop, and we used to use tungsten carbide inserts to cut metal and things like that. Pretty fun stuff. All right, that now is really the end of class. Thank you for being here. Please stay caught up on your stuff. We're going to be moving into week 3. Well, at the end of this week, we're finishing up week 2, and then we'll be moving into week 3. Let me know if you have questions, if you're struggling with anything. I saw, Joel, you had that question. If that didn't answer your question, what I just said, please send me a message, and I'll be happy to help you with it. And I'll go ahead and destroy some more water. If you want to look at some more water being destroyed.